Artificial intelligence has traditionally lived in massive distant data centers, but a quiet revolution is moving these brains directly onto the tiny chips in our hands. Traditional cloud AI is like mailing a letter to a Michelin-star restaurant in Paris just to ask what to cook for dinner. You wait days for a recipe to be mailed back. Edge AI is like having a sous chef standing next to you. They can smell the milk carton and tell you instantly if it is spoiled, with zero waiting or mail delay. This is the power of Edge AI. By processing data locally, devices get zero latency, complete privacy, and eliminate expensive cloud subscription fees. Cloud AI runs on massive power-hungry servers consuming megawatts of power. Edge AI squeezes specialized neural networks onto tiny silicon microchips. While cloud servers cost over $100, Edge microcontrollers cost just $50 to $0 and run 100% offline. In critical moments, latency matters. Sending data to the cloud takes 250 milliseconds. Edge processors make decisions under 2 milliseconds. This requires smaller models. While cloud AI models occupy terabits of storage, Edge AI models are compressed to fit inside a few kilobytes of memory. Traditional microcontrollers are slow at running AI. Their standard cus must calculate complex math grids one number at a time, wasting energy in slow loops. A TPU is like a silicon abacus where the beats sit in a mathematical grid. You feed the grid of numbers in, shake it once, and the answer falls out instantly. Traditional microcontrollers run simple appliances like microwaves or washing machines, but they struggle to process heavy neural networks. TPU microcontrollers solve this by placing a dedicated neural network accelerator block right next to the standard CU core on the same chip. Think of a regular CU as a single factory worker. If they need to build a car, they must fetch the doors, screw them on, fetch the tires, doing one task at a time. The TPU is like a heavy-duty stamping machine. The CU hands the math grid over, the TPU stamps it out in one cycle, and hands the completed answer back. Modern edge chips like the Max50 8000 or the Coral Micro use these built-in accelerators to run neural models in microseconds on milliwatts of power. Inside the micro-pony, rows of mathematical processors are hardwired together to route numbers through matrix arrays without standard memory delays. The biggest challenge is memory. Microcontrollers have less than 1 megabyte of RAM. Fitting a standard neural network onto one is like packing an elephant into a suitcase. To fit them, engineers use three TinyML compression techniques: quantization, pruning, and knowledge distillation. Quantization converts complex 32-bit decimal numbers into simple 8-bit whole numbers, reducing the mathematical precision to save memory. This shrinks the model size by 75% while keeping accuracy nearly identical, letting complex networks fit onto tiny microcontrollers. Imagine a carpenter measuring wood to the nearest inch instead of the exact millimeter. The furniture still functions, but the blueprint is much simpler. Pruning identifies weak, inactive connections inside the neural network and cuts them out completely, reducing the math required for each run. By setting weak parameters to 0, the hardware can skip those calculations entirely, speeding up local processing on the micro-TPU. It is like trimming dead branches off a tree. The tree takes up less space and is lighter, but the core trunk remains completely healthy and functional. Knowledge distillation uses a giant teacher model in the cloud to train a tiny student model to mimic its decisions using far fewer parameters. It is like a master chef condensing a 500-page cookbook into 10 golden rules for an apprentice. The apprentice gets 90% of the results with 1% of the reading. To run for years on batteries, edge chips use a wake-up hierarchy, keeping high-power modules off until they are explicitly needed. Traditional wireless cameras die in a single day if they keep their Wi-Fi and processors running full-time. The wireless connection is a massive power trap. In stage 1, the CU and Wi-Fi are shut down. Only an ultra-low power sensor remains active, consuming less than $1 worth of energy per year. Think of a guard dog sleeping on a porch with one ear open. It ignores the rain but wakes up and barks only if it hears a real suspicious sound. When the sensor detects motion, it sends an electrical pulse to wake up the local 2-bit coprocessor. The high-power Wi-Fi module remains asleep. The 2-bit analyzes the event locally. If it is just wind blowing a tree, it goes back to sleep. If it is a real person, it triggers the next stage. Only when a threat is confirmed does the 2-bit wake up the Wi-Fi module to send an alert, ensuring the power-hungry radio is rarely used. By keeping the Wi-Fi asleep 99% of the time, the camera can run for years on a single CRUD-20 32-coin battery costing just $0.50. This saves massive operating costs. Cloud cameras require continuous server connections, costing between $5.00 and $15.00 per month in subscription fees. For 100 camera system, cloud servers can bill usage in $0 annually. Edge cameras only cost as $500 in one-time hardware, saving businesses thousands. Edge is already at work. Soil sensors monitoring crops offline, smartwatches tracking heartbeats, and vibration sensors predicting factory machine failures. Smart light switches now process commands locally. Because they don't need the cloud, they turn lights off instantly, even if your home router is unplugged. At Laymans field, we believe that understanding technology shouldn't require a doctorate. We break down the engineering behind these breakthroughs for everyone. By bringing intelligence onto local silicon, Edge is creating a faster, private, and low-power future. Thank you for watching Laymans Field. We hope to keep bringing knowledge for everyone.